Theorem 3 is the last property, and it's kind of a really neat property. It's the generalization of theorem number 2. It says if we have a set of m vectors inside the real vector space Rn, if m is greater than n, so here little m and little n are integer values, positive integer values. If m is greater than n, this set S is linearly dependent. So what Theorem 3 is saying in a roundabout way is the highest possible number of independent vectors we can get in the vector space Rn is n. Here's the proof of theorem number 3. What we're going to do is we're going to set up each of these m vectors. Okay, each of these vectors has n components because they're in Rn. So v1 we're going to have components v11, v12, all the way up to v1n. And we're going to do that for every single vector all the way down to vm. Vm is going to have components vm1, vm2, all the way up to vmn. The next thing we're going to do is we're going to take a look at the independence equation. So here it is. The zero vector is equal to a1 v1 plus a2 v2 all the way up to am vm. When we plug the vectors in and we simplify, we get the following linear system. So what we do is we get all of the first components of each of our m vectors in the first equation. So if we were to scroll down all of the first components, we'll get v11a1, v21a2 up to vm1an. All of those components added together must be equal to 0. Do the same thing for all of the second components. That gives us the second equation. And we keep going until we get to the nth component, and that gives us the last equation. So what we have is we have a homogeneous system where we have m variables, a1 up to am, and we have n equations. So this is an underdetermined system. We have fewer equations than we have unknowns. And because we have homogeneous and underdetermined, this means we're going to have a non-trivial solution, or that S is linearly dependent. Most vector spaces, you can use all of the previous ideas in order to determine whether or not a set is independent or dependent. The only time we're going to run into a little bit of trouble using the other method is for the space of continuously differentiable functions. So for example, if we take Cn-1 from minus infinity to positive infinity, what do we do for independence and dependence then? Well, we have to use a special determinant, and it's called the Wronskian.